So next up, we have Vladan Nikolic with Riding the Wave.
Thank you very much. So, hello everybody. I like to see a lot of people. It is interesting probably that people are still drinking rakia from last night. So I hope soon they will show up and as soon as they are awake, and it will be fun for them, because in the end we will have big beep which will wake them for sure. So what are we going to discuss today? A lot of stuff. We are going to make this like introduction to SDR, software defined radio, which we use a lot during the IoT work. So we are going to show you a little bit of theory and a little bit of practice, and I hope in the end we will have enough time to do a little bit of demo to demonstrate how it actually is used in real life. So a few words about me. I'm leading the IBM X-Force Red European team. Our team exists under this name for more than 2 years, but a lot longer than that without the proper name. So we were part of IBM for 10 years, doing a lot of stuff. My personal expertise is electronics, embedded IoT, and SCADA stuff, and I like to hack vehicles. And also we are doing SCADA stuff, which also use a lot of radios. So that is interesting when you capture stuff on the long pipelines that nobody expected that you can do. So we'll start with short history of radio because it is fun, and I believe that you already saw those guys in the hallway just when you enter the premises. On the right side there is a radio club from Zrenjanin showing all the equipment of radio, and they were having some demonstration last night. So who invented radio? So actually radio waves exist since the Big Bang. So first Big Bang generated electromagnetic waves, but we as humans are unable to detect those waves except in some short range which we call light. Other than that, we are not aware of existence of radio waves because we don't have sense that can detect it. So first knowledge, actually first idea of radio waves came in 1860 some years by the work of Maxwell, and his 4 equations of electromagnetism actually predicted possibility of electromagnetic waves. And German Heinrich Hertz is the first one who actually demonstrated the electromagnetic wave in nature. After that was almost 20 years after the Maxwell predicted them. After that, we will wait a few years before our beloved Nikola Tesla actually created first use for these radio waves by creating a first radio-controlled device. So receiver and transmitter, which were used to control this boat here, which he demonstrated in US in almost 1898 or 9. So at the end of the century. So this was the actual first use of electromagnetic waves to control and to communicate. Tesla had he was genius, but he had one issue here. He didn't believe that electromagnetic waves can be used for long-range communication. He believed that they are limited just to line of sight. So he was more thinking about how he can transfer power via electromagnetic waves, but not communication. So the guy who came after him, Marconi, is the one who actually saw this possibility, and he is the one who made the first transmission of radio waves over the ocean. And later he had granted patents, but unfortunately in 1943 his patents were invalidated because they proved nothing new. Everything was based on previous work of Tesla and Maxwell and Hertz and other scientists who were doing research on the electromagnetic wave of that time. So we are now going into new century, and as a human species is unbelievable species. So our progress comes from our wish to destroy as much of rest of our species as possible. So the wars and military are usually drive the progress. So World War I was the beginning of the century. So first use of radio waves are there, but problem with radio waves, they were not very useful. Why? First thing, radio devices of that time were really big and unreliable. So it was not possible to use it on the front lines. they were breaking, they were big and heavy to transport. And the problem is cryptography at the time was not on top. So it was easy to communicate with guys you want to communicate, but everybody else was also able to capture your communications. So we needed to wait a little bit more of cryptography development for radio to become really, really useful as we see it today. So it was used during the World War I, it was used mostly as a remote control for torpedoes. And we have demonstrated, there was demonstration about American ship which was radio controlled completely and who could target other vehicles, other ships actually. So after 20 years we have Second World War where we already have radio in almost every home. And it was used mostly in propaganda purposes during the World War II. But we already see that the Germans actually did a lot in development of radio waves technology because they wanted their airplanes and missiles to be very effective. So they developed a lot of radio technology that we are seeing even today. And during the 1941, I believe one of the big discovery was made in US and done actually by one German who was in US at the time, and who enabled our use of Wi-Fi today. Anybody have idea who invented what? Zoz. Yeah. But this is unfair. Okay. So Hedy Lamarr, she was an actress in Europe before the war. In 1938, I believe she ran from the war to Germany, to US, and she wanted to make these missiles more controllable and to make it more resilient to tampering and overhearing. So she had an idea based on an old piano which was doing automatic stuff, and she used the help from a guy who actually made pianos to create first frequency hopping technology in which receiver and transmitter would simultaneously hop through different channels and to make any eavesdropping more difficult. And this is technology that we are using today in our wireless techniques to jump from channel to channel, so it enables all of us here to be connected to the same wireless spectrum at the same time. After the world wars, we saw a miniaturization and appearance of solid devices like tubes and transistors and integrated circuits, and that made use of radio waves in our everyday life. So I have here a few pictures taken from these guys in the hallway, and this is a big receiver. I don't know if you can see that tubes are actually glowing, so it is receiving at this moment. So it is very interesting piece of equipment, and this is developed somewhere in 50s, I believe, if I recall correctly. But as we see, usage of radio is expanding, and I believe in this moment everybody of you has at least 3 radios on you. So you have Bluetooth radio, you have GSM radio, and you have wireless radio in your phone. So 3 different radios. And what is the problem? So if you want to hack such stuff using this old technology, it was really difficult to do. First, because on high frequencies, absolutely everything is antenna. So even your solder joints can be antenna. So it is easy to have oscillation and to have a lot of problems everywhere, and to have low quality of receiving the emanations, and that would make it really difficult to actually analyze the content of what is transferred over the waves. So in order to help us with this, we needed a little bit of progress. So hardware was not enough. First idea was, okay, let us put all these different receivers into one box and then use a software to decide which box is active, so which function is active. So we have software-controlled radios at this point, where you control it. Amplitude modulation, frequency modulation. Software can choose and activate hardware for that, but hardware had to exist to be able to use it. We can switch frequencies through software. We can switch gain. We can control filters, but it is all implemented in hardware, and software is just providing control and selection. So it is not, still you need to develop hardware. So this is what caused first appearance of software-defined radio. During the 80s, there was a lot of research in this area. Again, military was leading this because it was not very easy to have a lot of different equipment on the front lines. So it is easier if you can go with the small devices. And the idea behind this is we will have a radio which all definition, all functions will be implemented in software, and hardware will only be there to transmit and receive this information. In 2010, we gained a first cheap and usable SDR. So before that, only military had access to this technology because it was really expensive. In 2010, kernel developer called Eric Fry was trying to create a driver for Linux for these small DVB sticks that he had. And he had a problem with them. And in order to analyze what is happening, he started debugging them. And when debugging on Windows machine, he saw that if you put this chip in a debugging mode, IQ parameters will be transferred directly to your computer via USB. And we got first cheap RTL dongles, which are now everywhere. So how is this, what is this IQ parameters that are sent? So first idea is every wave can be sampled into two times more than frequency to gain the amplitude and frequency of the signal. So that's Shannon theorem for selecting. But if we do it a little bit differently, thanks to this small math here, which is simple, we say that every phase modulated signal can be represented by two components which are 90 degrees off the phase, which is called quadrature. So if we sample the signal in 90 degrees with two samples which are 90 degrees in phase, we will be able to reconstruct this signal. It is not exactly 100% sure correct when you have amplitude modulation in addition to frequency phase modulation, but it is close enough for all practical purpose. So this is why we call it narrow band signal. So for it is okay for narrow band signals in which modulated frequency is much lower than actual carrier frequency. So thanks to this math, we have two components, I and Q. I is in phase component and Q is quadrature component, which is 90 degrees moved. And this enables us to reconstruct every possible signal in our software model, in algorithms. So this is what actually makes SDR possible, this simple math. So thanks to this, we now have a lot of different devices which can actually be used to transmit and receive radios. So we have, I believe for $10, you can order from your favorite Chinese supplier delivered. And problem with these devices is they are listen only. So they can receive signals, but you will not be able to inject signals back. It is easy to overcome. If you have Raspberry Pi, by addition of small wire to port GPO18, which is PWM, hardware PWM, you can make Raspberry Pi to actually inject electromagnetic waves back. So by combining this with a very, very cheap device, which you have already, you can actually retransmit. So this is very common used for sniff and replay attacks. So you will see later that if you have a knob, for example, for car, some of them are not implemented properly. So if you're just listening to right frequency, you can capture the signal to unlock the car, save it, and replay it later. So you can capture with this and replay with your Raspberry Pi with just additional wire, and it will unlock. So receiving only is fun, but obviously we want to have ability to also inject signals. Thanks to Mike, who developed HackerF1, we actually have a relatively cheap device. I have one here. It is very cheap, very small. I have it always with me because it is really non-intrusive, and it's very useful because it can also receive and transmit, but not at the same time. So that is the only limitation of the device. It cannot do it at the same time. So it is half duplex device. but it has everything that you need in it. And if you really need full duplex, and we will show why we need full duplex devices later, there are Blade RF Ethos or a lot of new devices that are currently being developed that you can actually use to accomplish both receive and transmit functions at the same time. So as you see, this box is really small, it fits into my bag, and I never have problems on customs. I have problem if I try to put this, but no problem with this, and with this I can overtake the airplane actually. With this I can just drink it or spit water on you, whatever. So this is our perception of risk, that's the problem. I have here a large picture of HackRF because I really want to go through how this actually works, because it is really important to understand how it works in order to be able to use it effectively. As any tool, you need to be aware of its limitations in order to understand what you actually are getting. If it is problem with the tool, or it is problem with the process, or it is something else. So now you are going to see how antenna can be really, really useful, even if we are not transmitting or receiving anything, because it can be extended to almost 1 meter, and I can use it to show or to beat you if I really need to. Okay, so here, this is first antenna.
You take the hand mic, otherwise it's not on the
Okay.
batteries on that.
Yeah. Okay, so I will have to be really loud. Let me try this. If I
a laser, I think, on the thingy, so it's easier.
where is the laser? But how can I beat people with laser? No, I don't see lasers. So I will use stick with this. This always works. No need batteries. And I talk loud. If you cannot hear me, just yell and I will repeat. So first we have antenna connector. From this, this is connected there, and it injects all electromagnetic waves which are
It was nice.
Excellent, this works. Laser. New technology. This is more fun. I cannot beat you with this. So let me see which button. Woo! Excellent. So I don't need this then. Excellent. So thank you. So just don't forget to pick it up later, because I will forget to return it. Sure. So we have antenna connector, and we have this passive. I need microphone. Okay, let me try to synchronize. I'm still thinking about my antenna. Okay, so yeah. Can you hear me now? Yes. Excellent. So we have antenna, and we have few passive devices here which are just used to condition the signal that we are receiving from antenna. We know. You know that antenna must be matched to impedance of the input amplifiers in order to avoid problems. And then we have first step in our process, which is this piece of hardware here. This is all actually RF module, and it processes radio frequency module. So the signal comes to this local oscillator, and it is down mixed to 2.2 to 2.7 gigahertz. So whatever frequency we are capturing here, it will be shifted to this range, 2.2 to 2.7 gigahertz. And then after that, it will be processed by this baseband transceiver, which will actually pick up the signal, do amplification, filtering, and whatever needs to be done, and move it from this intermediate frequency to baseband frequency. Baseband frequency is close to 0, so it is actually from 0 to whatever number of samples per second can this device give. And this device is actually quadrature ADC and DAC. So when your signal comes in, it goes here, 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 and then comes here in analog mode. This device here will convert your signal into I and Q parameters very quickly and provide it to the bus. This device here is a big Xilinx FPGA, which is actually doing acquiring. So it is really quick, and it is used to synchronize all communication between computer, which is connected to USB port here, and the radio receiver here. So this is main device used for control. This is glue logic between the analog world and the digital world. And we have big ARM core here, which controls the complete process and provides USB communication to the computer. So we have radio frequency signal here, and it enters there and exits here as I and Q parameters transferred over the USB port. So when we are doing sampling, we are pretty much limited by speed of USB port. So in this case, since we have USB 2, that is about 21 megasamples per second, and although this device here can provide a little bit more, this is practical limit. So you will never be able to do more than 21 megasamples per second, even in ideal conditions. So we are saying 20 megasamples per second is what is expected. So that gives us 20 megahertz of bandwidth that we can scan. And when we are going the other way, so when we are producing the signal, we are going to inject our I and Q parts here. It will be processed, transferred, converted to analog, converted to radio intermediate frequency, and then this chip will be putting it into the expected frequency and send it to antenna. What is the problem? So when we are receiving stuff, it's not really a problem. If our antenna is not matched properly to our radio parameters, it will create bad reception, but that's it, usually. Only problem is if you have too strong signal here, we might make some damage in this part here. But when we are transmitting, and if we turn on gain, we can actually do a lot of damage because antenna must be better matched to avoid having power reflecting back into the RF circuit. So we need to be a little bit careful, especially when we are doing sniffing. If you are too close, we can actually fry our circuit. So avoid setting gain in the beginning if you don't have to. So keep the gain to the lowest limit possible. And there is other problem with gain is that usually we are not licensed to transmit on specific frequencies. Later we will go through some of the frequencies, and you will see that we are allowed to transmit only on 27 megahertz, which is called citizen band, and everybody is allowed to transmit without license. All other are usually heavily regulated, and you are not allowed to transmit without proper shielding and minimal to avoid any interference with real devices out there. Okay? Is there any question about this part so far? You're sleeping? Okay, nobody need to be beaten. Okay, excellent. Okay, so now we have our hardware developed, working, and now we need a little bit of software because our radio is all defined in software at this point. So in order to make it work, we need a piece of software. So the one that is most commonly used and most versatile is actually GNU Radio Companion, which is available, I believe, in almost every Linux distribution that I have seen so far. And it is actually a very great tool because it enables you to do development like Lego. So you will just pick up your boxes and put the boxes on the screen, connect those boxes, and you will have a result. Okay, you need to know which boxes and how they are going to connect them, but that's another story. So I have here shown the simplest possible script, which have just one source, which is my SDR, and one sink, which is this waterfall plot. And this is actually showing the most interesting part of the spectrum. This is 433 megahertz, where we have a lot of IoT devices communicating. And we see in this waterfall plot, we can see that the higher the power, the color is upper. So with green, it is somewhere in the middle. If it is red, we have a very strong transmitter. So if we don't know where is our device, we can just scan the spectrum and discover it by checking the power when the device is on and off. And to make this process more efficient, we need a tool called Spectrum Analyzer. Spectrum Analyzer is the tool which will scan the range of frequencies for you and map the power of the receiving signal in time. So in this, there is a tool called Cure Spectrum Analyzer, of course. It supports HackRF since recently, since almost 2 years actually. And I'm here scanning the full range that is possible with this device, and that is up to 6 gigahertz. And we can see few red stripes in a lot of blue. So I don't know if it is easy to see. In this area here, we have tiny speckles of red. Any idea what is here? Wi-Fi, yes. We have this large piece here in about 5.1 gigahertz. That we have something here in 2.1. What is that? 3G, yeah. We have mobile telephony in a lot of places. We have it in 850 to 90. We have it 2.1 gigahertz, depending on in which country you are. So, and you can also see that lower frequencies are full with different communications. There is a lot of red. So I pull up here. This is, I think, up to 100. Yep. 200 megahertz, and we'll see toward the end of that we have a lot of transmitters which are very strong, and that would be FM stations. And we see beyond that we have a lot of stuff in low frequencies on 27 megahertz. That is a band that you can use to transmit freely. You can find radio amateurs in a lot of, they have 20 meters, 16 meters, 10 meters bands where ham radio operators are using to transmit and receive. So we have a lot of spectrum. And sometimes if we don't know what our device is working, we need to do the scan and to find where the device is actually generating electromagnetic waves, in which band. There are tools which can help with decoding. So if you manage to capture your electromagnetic waves, you need to be able to analyze them and to collect information which is actually transmitted over those waves. Here you can see this is different FM stations, and this tool is called GQRX, and it can automatically do some decoding for you. Amplitude modulation, frequency modulation, telegraph. So a lot of stuff can be decoded by this tool automatically. So you just position your filter, select frequency, and you can hear the radio. So we will. Can you turn on the microphone? So I have stuff ready here. So I know the frequencies, so we can see here that we have microphone is turned on and it is receiving.
Test 1, 2, 3.
Okay, so now I will start decoding.
Testing 1, 2, 3.
Okay, it's too quiet.
Too quiet.
My laptop is too quiet. It's generating, but it's never mind.
Okay.
So, but you can see how when he's talking, we see a lot of shifting. So this means that it is some kind of frequency modulation, probably FM. And now he's silent, and we are on base frequency. So it is relatively easy to analyze what you are getting. But unfortunately, this laptop is too quiet to show you this in real. This can be a lot of stuff. So you sometimes have different transmitters and receivers in the same range. So we can also capture that one. Just position the cursor to frequency of that device. Why you are not going to move? Let me see, I lost it. It is some sideband of the microphone. So when he turned off the microphone, he disappeared. So it was some reflection somewhere. So that is the problem with radio waves. They have reflection, they have different channels everywhere. So sometimes That was SDR Sharp. That's Windows tool, because on this machine I have only Windows, unfortunately. And these devices are not working really great with virtual machines, because you need high-speed USB, and if you are doing anything serious, don't use virtual machines. It's useless. Okay, so you can listen actually to a lot of different stuff by this. I have few guys near my home, and they are really funny, and they talk to each other almost each day. And whenever I'm bored, I just tune to their frequency, and I laugh because they are crazy. And I'm not sure if they are aware that anybody else is listening to them, but they're crazy. There are a lot of different software. So when you capture, you sometimes need to do decode of your signals. There are some tools which will help you. One that I like the best is in Spectrum. So when you have, this is some frequency modulated signal, we have two frequencies: when device is on, then off, then on. So this can be something like OO key, so on-off keying. When you press the button, you have one frequency, and when you release the button, there is nothing, or something like that. So with this device, you can easily analyze the spectrum, and you can actually decode by positioning the cursor and providing some additional information. You can actually get the signal reconstructed. You can also do the same with GNU Software Radio. So everything that we are seeing here can be done with GNU Software Radio, but problem is in GNU Software Radio, you really need to know what you are doing. But it is really versatile, and you can create decoders for absolutely everything after you become aware what you are decoding. There is a baud line, which is very good for analyzing spectrum. So when you capture some spectrum and you want to discern if it is specific kind of encoding, so it is quadrature or B-phase key shift or whatever, this is a tool that can help you great. And one of my favorites, it is Ultimate Radio Hacker. That tool will do everything for you automatically for protocol that it supports, and it supports a lot of protocols. So and with this tool you can actually do a fuzzing of the radio waves. So it supports fuzzing. So that is something that I find really interesting in our normal work. So now we have hardware, we have software, and we have an idea of device that we want to access. But where are we going to start? If you were here before we started presentation, you might overhear my conversation with those guys when I was asking them which frequency your microphone is emitting. And he told me, oh, 635. Because at this moment I cannot retrieve this information. But usually if device has FCC ID on it, it is possible that FCC has documentation on it. FCC mandates that every device which emits any kind of electromagnetic waves must be certified. And in order to get this certification, you need to provide a lot of information about your device, including pictures of the boards, electromagnetic spectrum. You need to specify which protocols are used, how you are encoding information, and you can find a lot of information. And the best part is you can find this information even before device is on the market, because device will get certified before it enters the market. So if you plan to test any device, you can discover this information and be ready. So when device is on the market, you can be really quick to discover problems with it. Sometimes you will discover problems even before you have device by just reading documentation. And problem with the FCC site is it is really difficult to navigate. It is nightmare. So there is a guy who created FCC.io site, which actually has only search box that you can use for searching. And it will provide you, it will go for you on the FCC site, search for information, and provide you direct links. So you can just click on link and get your reading stuff. But there is a lot to read. But it is necessary because it will help you tremendously to lower the time you need for analysis of the device. Okay? So when I set up my stuff, first thing that I like to do is actually to follow the planes. And my kids like, because my home is near to landing strip on the Belgrade airport. Actually, it is an approach. So we have airplanes no more than 2 kilometers above us, and ILS signal goes just across our building. So it is very common for us to hear airplanes and kids, oh, what is this plane? What is this plane? And sometimes if I have time, I just put my HackRF on the window and I set up everything I need to spot the planes. Why it is possible? First thing, planes have a lot of radios in them. I already mentioned ILS. ILS is Instrument Landing System. It is used to help airplanes land on the runway. So it is guidance, it has two radios. I'm not going into the details too much. So it has ILS, it has VOR. So there is possibility for airplanes, even before there was GPS, they had to navigate. So there was a system of radio transmitters over the planet Earth, which are known frequency, and you can find them in Jepsen maps, and you can use them to navigate. So there is a radio in airplane which receives this navigational data. And of course we have GPS. But this ADS-B system is mandatory on all new airplanes, and it is giving position and call sign and a few bit of details about the plane as it flies. And control towers using this information as a secondary source of information in addition to primary radar. There are some talks that some of the control, aerial control will change this, and instead of using radar as a primary, they might switch to ADS-B as a primary source of information. However dangerous it is, because its signal is at very easily found at 10 and 90 megahertz. It is pulse position modulation, so by just position of pulse you decide if it is 0 or 1. It is not encrypted and decoded fairly easily, and there is a lot of information. I'm not aware, I know that guy created injector for this, but he is keeping this code private. But it is not too difficult to develop. And imagine that fun if you start injecting ADS signals back into the airspace, how fun it would be. We spoke with Aerocontrol, and they told us that it should not be possible, because they say so. They never go into details how they are preventing this, but they say it isn't possible, it is illegal, and why you are asking that? Are you criminal or something? So it is simple thing. I have here captured, I'm not sure how if you see it, because this is unlucky choice of colors, but this is you will see there is a big yellow line and streaks as we have pulses. So it is really easy to spot and to analyze this information. I have here as an example decoding block in GRC, and there is a standalone tool, dump 1090. You could see this tool running on the stand there. Last night they were tracking some planes, and they have big antenna somewhere on the roof, and they have a lot of planes. I have here only few, but I didn't have much time to capture them. So you can see different of information we have. We have velocity of the plane, altitude, position, call sign, so we can map it on the map, and we know exact position of the plane. And problem is that there are some other radios in the airplane which are using this information also. There is a so-called traffic collision avoidance system in every big airplane, which is using this data in order to verify current situation in a nearby vicinity of the plane and to try to prevent crashes. So two planes to avoid crashes. So there is automated systems which will trigger alarm and take action based on this information. So if we go back to injecting this information, if we add that into the picture, it might be really dangerous to be able to inject this information. Then we have ACARS system, which is older version of ADS-B, because not all planes are new planes, so we have a lot of especially amateur planes like Cessnas, like Utvas here, which do not have this system. They have older ACARS. It is a simpler version of ADS-B, and it is also easy to decode and track. It is amplitude modified signal, modulated signal, and it uses 131.5 megahertz for communication. Okay. So, those you still there, yes? You ruined my presentation yesterday. Yeah. So for a project that we were doing, we had a device to test an IoT device, which is used to transmit, among other stuff, also location of device in order to control the target. So the idea is to enforce geofencing, like on dogs, for example. So when you want to know where is your dog and to know if your dog ran out of your yard, so you can put him on collar, small device, and you can also set in the application a perimeter when he's allowed to go. And as soon as device leave this perimeter, you will get alarm that your dog ran away, or even in some sadistic cases, you can shock the animal or what. It is used for training of big and dangerous animals, not on dogs, I hope. So we needed to verify a lot of stuff. A lot of stuff was related to radio devices, and among one, it was GPS. We did this somewhere in 2015 and 16, so we didn't have a lot of information, and unfortunately the tool that we have now was not mature. Actually, we didn't know even existed in that time. So we needed to analyze GPS system and to analyze and to understand it in order to create tools that we needed at the time to spoof the position. So all these pictures are generated in the last few days, so they are not. But the idea about GPS system is that by knowing your position of few stationary locations, and by knowing your exact distance from these stationary locations, you can triangulate your own position. In this case, we have 34 satellites which are currently deployed. Although I believe 30 or 31 is actually needed, and the rest is spares in case of malfunctions or needed to do some maintenance on them. You can just move another satellite in place of the one that needs to be worked on. And you need actually to see only 4 of them to get precise lock on your position. But as everything, the more you have, the better precision you have. And in order to have stationary satellites are not stationary, they are going circling around the planet, and we are moving around the planet. So in order to know exact location of the satellites, our receivers need to have this data. So this is called almanac, and it is created. Devices downloading them. Our phones can use wireless to download almanacs from providers. So that is when you have assisted GPS. So you don't receive this information directly from satellites, but receiving them from providers. And you need to have precise time measurements. So this is what is needed. So when you have, we will see later on the section. So we need to have this information to be able to locate. Every GPS satellite emits 2 signals. One is for public use. So this is the one that we are using. And there is another one which is for military use only, and it has protected access. So GPS signals are emitted on 2 frequencies, 1575.42 megahertz and 1227.60 megahertz. And we have a CA code. It is course acquisition code. It is the first signal that your device will capture from the satellite, and it will provide ability to locate other satellites. So during this code, you will be receiving ephemeris table for this specific satellite and almanac for all others. So it will give, every satellite know where are the others, so they will transmit this information to your device, and it takes about 1.5-2 minutes to transmit this information to your GPS receiver. So this is why when you turn on GPS, it will not locate instantly, but it will first need to verify time on multiple satellites, because we do not have atomic clocks in this. Otherwise, this would cost probably 100,000 euros, not 1,000 euros. So we have only simple crystal clocks in this, and on satellites there are real atomic, very expensive clocks, which are very precise. And by using some communication tricks, this device will synchronize to that clock and have exact time. And after acquisition of first satellite communication, it will download the ephemeris table of that, and it will know location of other satellites. It will quickly connect to other satellites, take ephemeris tables which are precise. So almanac is just rough. Ephemeris tables for a specific satellite is very precise. It will collect all this information, and after 5 minutes, as we saw yesterday, your device will have full lock and know its exact position. So by spoofing this satellite signal, we can make device believe whatever we want. As Zoz showed you yesterday, it was easy to spoof a signal and to convince drone to land because it thinks it is somewhere very far away. So we did something similar, but we were sitting in UK, and we convinced device that it is actually in Egypt, in Cairo. So it was very funny because when we did this, I had my phone turned off, but my colleague, who was unlucky, didn't do it because he had iPhone and he couldn't disable location service, and he was locked on the Egypt. And problem was that after this we needed to go back about 100 kilometers to have a meeting with the customer. So idea was, okay, we will sit in the car and go, and he started to navigate, and his navigation is still locked to Cairo. Okay, we have a problem. Okay, he knows first half of the way, so we are, okay, let us start. Unfortunately, I didn't have GPRS because I was in roaming, and I couldn't use my navigation, so we were in a bit of trouble, but in about half an hour, his device recovered, managed to download proper ephemeris tables and synchronized clocks and everything, and we managed to navigate second part of the road without problems. We did our meeting, we had everything. He came home, and about 10 p.m. he called me, why my weather say it is 30 degrees and it is November in Portsmouth, it is -1 degree outside. Sorry guys, I don't know what happened. So it is really, it can be really funny, and this is actual real log from device after we had locked. So you see that it was November, it was -1 outside, and device was 100% sure it is somewhere outside of Cairo. So as a consequence, this is actually a picture of weather that my friend had on his phone at the time. So you can see that we have changed our position from, I think, something to something else. So, yeah, by just spoofing the position. What we also notice is that time is a little bit different than we expected it to be. So this is the picture I took yesterday while helping Zoz prepare demo. So it was 17:05, but GPS time saying it is 3 minutes after the midnight. And yesterday was 15th, not 14th. So for all practical purposes, if I allowed my device to synchronize time to GPS time, not to GSM cell, I would have completely wrong time on my phone. And imagine some financial institutions are using actually NTP servers in their infrastructure to synchronize the time, because there are regulations which say that banks or all other financial institutions must have precise time of transaction up to 100 milliseconds. And they are using NTP servers which are connected to GPS receivers, very common. So GPS receiver provides authoritative time for financial institution. So if we generate this signal near their antennas, it will be fun. So I didn't find bank which will allow me to test this yet, but I work on this and hope that I will have a little bit more information for a few years when I'm out of jail. There are some stuff that you can do to prevent this kind of stuff by monitoring your device and don't allow unexpected jumps. So if your device is 1 minute in Portsmouth, the next minute in Cairo, there is some error in the system. So you need to be a little bit more resilient to this. Also, this device had other sensors which can help prevent this. So we will discuss them in the next step. So we learn not to trust GPS, but we usually don't think a lot about our phone. So our phones are trusted devices. We put all our secrets on it, our financial stuff. We could use it for online transaction. We have payment information. We have our health-related information. We have our scans of documents. A lot of stuff we keep in our phones. But how it is secured? So problem here is not very good. That's the problem. So we will not be talking about how device applications are developed. That is for web application guys. So we are going to speak about communication. So this device that I mentioned has GPS and also have GPRS communication. So in order to provide information that it collects, it needs to connect to some cloud-based infrastructure and to provide this information there, and your mobile application or web application will show you information that is collected in the cloud. So you can see where is your device, what is the environment, how quickly it moves, everything. And device is communicating without wires. And we found that there is GSM SIM card integrated on device. And it was accessing some private access point. So there was custom SIM card, which was issued by some providers which offer global GPRS service. So in whichever country you are, it will be, it will work, except in Serbia. For some reason in Serbia it doesn't work. So that was the problem with the testing, because I was back from UK and I needed to test it in Serbia. So what I can do? So I decided to spoof GPRS access point for it. So using Blade RF and the 8 BTS, I created a specific cell which I control. And by analyzing firmware from device which we have successfully dumped before, we discovered what is the APN and which credential device is using. By analyzing integrated SIM card, we discovered the mobile network and the mobile country codes, which we needed to set up this fully. So device thinks it is in its native network. It sees its APN. It can authenticate to APN, so it can communicate freely. But on the other exit of that node is through my machines. When I sniff the traffic, I redirect the traffic, I manipulated traffic, and I did all the bad stuff to this traffic, thanks to not properly implemented certificate pinning, not certificate verification. They were trusting their APN is private and nobody else can spoof it. And problem with this, we were locked only to 2G networks. That was a problem at the time. There was not possibility to simulate any other network. I believe now they say they support LTE also. I haven't verified it, but I will try soon because they asked us to do this again. So we will probably be checking if it is possible to support this. So as a result of this sniffing of the traffic, we actually managed to collect information which devices used to connect to cloud infrastructure. So we managed to discover authentication details, authentication scheme, authorization scheme, and we were able to do whatever we wanted. We discovered the algorithm they used to generate all of these based on the device serial number. So if you know device serial number, we created some Python scripts that you just enter serial number and you get everything you need. So you can just emulate this device and tell to guy who is looking at his phone where is his device, that his device is somewhere completely else. So we didn't even need to spoof GPS. We can just intercept MQTT traffic and do whatever we want with it. So I guess we are almost done. So just one more slide. So about GSM sniffing. So I showed you how you can sniff when you can inject yourself as a rough node. There is other possibility which is much more difficult because you need to know exact channel on which device is communicating. And using GRGCM and Wireshark, you can actually sniff communication, including voice and SMS traffic that goes from the phone to the devices you are using very weak encryption, A1 or A5, which are all broken, and there are decoders for that publicly available, so it should not be a big issue of getting this. Okay, so thank you. If there are any questions. Me.
Just two quick comments. If you're a cheap bastard like me and you have Airtel SDR, you can calibrate its frequency using the GSM signals. Your clock in Airtel SDR won't be perfect, but there is a calibrate program which will listen to the GSM clock and give you the PPM of your local oscillator, which will make your Airtel SDR even better. And are you aware of FL2k, Osmo FL2k, the VGA DAC on USB 3, which is probably the cheapest way to generate signals? Very low power signals, but
You cannot beat one wire on Raspberry Pi by price.
that's true, but this is the alternative. Thank you.
Yeah, thank you. So you have here this tool. I also am showing it here, used for calibration. Okay. Okay, any other questions, comments? Yeah.
Yep, thanks for the presentation. Just a quick remark on the GNU Radio Companion. Basically, one thing that I would say it's also important to mention is that you can also write modules in C or in Python, and you can quickly add protocol decoders and this kind of stuff, you know, to this,
Yep.
I would say, well, to the decoding chain, to the end of the decoding chain.
Yeah, thank you.
Thanks.
One comment on the single wire on the Raspberry Pi. It generates a rectangular signal, so even if you are transmitting on a frequency where you are allowed to transmit, you will have enormous sidebands and frequencies where you should not transmit,
Yeah.
so be careful with that.
Yeah, it's using PWM, so it is dangerous, but it works. It doesn't have too much signal strength to be dangerous. You need to be really close. Okay. No more questions? Okay, thank you. And we can continue discussion later, so we need to